Alright, today we are talking about chords and arcs and all their properties and theorems that are associated with them. So a chord, we talked about that the other day. A chord is a chord of a circle is a segment with two endpoints on the circle, and a chord is part of what we call a secant line. Which a secant line, that is a line instead of a segment, a line that intersects a circle twice. Okay, what is the largest chord in any circle? Here's a picture of it right here. It's called a diameter. And that would be the longest chord you'd be able to draw. Any other chord would be shorter than that. So that would be the largest possible distance. And that's why we use diameter to measure circles. Like, I don't know if you've seen pizzas or whatever. Pizzas, they say, 14-inch pizza. That's, the biggest distance of the pizza there, essentially. Is a radius a chord? Why? So let me draw a radius. And here's the thing with the radius. Radius is from the center to the outside of the circle, and you need two endpoints on a circle. So I'm going to say a radius only has one endpoint on the circle. On a circle. So a diameter is a chord, but a radius is not. Okay. Theorem 12.4, this is out of the textbook. In the same circle or in congruent circles, two arcs are congruent if and only if their central angles are congruent. So here's kind of a picture of that, and actually the central angle is supposed to be kind of in the center. This one's a little bit off here. But you can go ahead and assume that that is the center right here. I'll put a C for that. If those arcs are congruent, then the angles are congruent. And then also, if the angles are congruent, then the arcs are congruent. Okay. Now, there's a couple extra theorems here, and these all kind of tie in with one another. So I drew one picture for this. Theorem 12.5, for whatever reason, we didn't get that typed out. But what that is saying is if you have two central angles, those that are congruent, they need to have congruent chords. It's like here's a central angle right there. Here's another central angle. They need to have congruent chords associated with them. So you take those two endpoints there, those chords that are across from those central angles, and those would be congruent. All right, there's also another theorem here. Two congruent arcs have congruent chords. So for example, if you have an arc right there that's congruent to an arc on another side, then the chords associated with them need to be congruent. So these all three of these theorems kind of tie into one another. You have congruent, really you can say all three of them are congruent. If you have a congruent central angle, then you have congruent chords and you have congruent arcs. There's all the converses of those. All right, next one here. If one chord of a perpendicular bisector is the perpendicular bisector of another chord, then the first chord is a diameter. And then I guess this is where I don't like this here. I guess you could say a radius, but remember a radius technically isn't a chord, so I really don't like that part there. But if you do see something that does make a perpendicular bisector and it's not a chord but it's a perpendicular bisector, you can say that it could be a radius there. So maybe we change either that word chord or we leave out the part about the radius there. Kind of the same thing here, a little different. If a diameter or radius is blank to a chord, then it bisects the chord and actually the arc. So if it's perpendicular. So in a way, it's kind of the opposite, I guess, or the converse of what we just talked about there. There's a couple of pictures of it there. Let's see. Oh, I think this picture, I was kind of looking at that for a second. I think that picture is leaving off the fact that it's a perpendicular bisector. And then if it's perpendicular to a chord and it bisects a chord. So they left off that. So that means these little pieces of the arcs could be congruent or these pieces right there should be congruent as well. So this is kind of a bizarre one. In the same circle or in congruent circles, congruent chords are blank from the center of the circle. So if I have a chord there of 12 and then another chord somewhere else of 12, then we say they are equidistant. So that means that shortest possible distance between the chord and the center, those two distances should be the same. So we call that equidistant. So now we're just going to use all the different theorems that we kind of talked about, I guess, here. So let's check this out here. You got diameter is 20 inches, solve for x. Okay, so this whole entire diameter is 20, so that means the radius right here should be 10. And it looks like you have a perpendicular bisector going on right there, so we're going to use Pythagorean theorem with those sides right there. So we'll go x squared and then plus 8 squared and then equals 10 squared. And the only thing that people tend to mess up sometimes on these is figuring out where all the different pieces go for the right triangle. So it's kind of turned around there, so just be kind of careful. The 10 is the hypotenuse, so be a little careful when you're setting them up there. I think that's 64 and 100, that's x squared, it's 36, or x is 6. And that's basically, it's a 3, 4, 5 triangle. Everything multiplied by 2 though. This one's kind of similar, I guess. Diameter 20 inches, solve for x. So I guess if the diameter is 20, that means the radius is going to be 10. So people usually draw that and then, or write that out, and then they kind of get stuck here. So they don't know what else they can do here. Because if you're looking here, it looks like we got a right triangle. And you got one side. And, you know, some people might say, well, it looks like it's isosceles, so maybe this is 5. And that could be true on this one example, but I'm not 100% sure on that there. But what we need to do here is consider all radiuses, no matter which way you look at it. It should be 10. And that includes these ones that are going diagonal like this. So those are both 10 as well. And that's what people forget about is, hey, we have a radius, so that means any of the radiuses, or radii, I guess, are going to be 10. So I'll redraw that. That's 10, x, 5, and then you can go and solve. And actually, I think those are the dimensions of, it looks like a 30, 60, 90 triangle, but we'll go ahead and work it all the way out. 10 is by itself, so that's 10 squared. Oops, 10 squared, and then equals, I guess, x squared plus 5 squared. So that's what, 125, so that's 75 equals x squared. And then you square root both sides, and it does come out to 5 squared to 3, I believe. Whoops, 25, 3, 5, 5. So 5 square root of 3 for your x dimension. We'll go ahead and leave that in simplest radical form just because we can. And that would be both of those x's there. Now if they asked you for this whole entire segment, you would just double that. Okay, next one here. Let's see what we got. Solve for x. So this one's actually kind of what I was just talking about there. So it looks like a radius is 6. Got another dimension is 4. And instead of finding the whole side, we need to find, or the, one side of this right triangle, we need to find the whole side. So what I'm going to do here on this one is I'm going to consider that y. Some people like to consider it 1/2 x, but then when you start squaring things, some of you guys mess up the rules. So instead of calling that 1/2 x, I'm just going to call it a different variable for a minute. So I'm going to call it y. In my opinion, that's a little bit easier to do. So we'll get y squared plus 4 squared equals 6 squared. Okay, so that's y squared, plus 16, and then I guess equals 36. Subtract, you got y squared equals 20. And then simplest radical form, I think, comes out to 2 square root of 5. Let me redo that. That is y. That is not actually your answer. That is just this half of it. 2 square root of 5. So then to find the full thing, we need to do 2 square root of 5 plus 2 square root of 5, or 2 times square root of 5. So anyways, you get 4 square root of 5 for your answer there for that full thing. So a lot of Pythagorean theorem with these, since we're going to be dealing with perpendicular bisectors quite a bit. Actually, number 4 is a little different though. So 4 right here. Notice first of all you have a perpendicular bisector right there going on. So this other piece here is 7. Therefore the whole thing is 14. Alright, and then since these two chords are equidistant, right there, we went over a theorem saying that those chords have to be the same, so this other chord has to be 14. And I think, you know, even if you didn't know that theorem by heart, that's probably what you would put there. It kind of looks like it. It's one of the intuitive ones when we see it, I guess. So that one, rather straightforward. Let's see what's going on with this one here. I guess we're trying to find x and y. X is going to be easy because it looks like we have a perpendicular line there, and this also goes through the center, so that has to be a diameter. Therefore, it has to be a perpendicular bisector. So x, that part's easy. That's just 5 square root of 3. Once again, that is because you start out with a diameter and it is perpendicular to a chord. So if it's perpendicular and a diameter, it has to be a perpendicular bisector. Okay, now also you have a right triangle in there, and apparently got 60 degrees. You got 5 square root of 3, and we can use what we know about 30, 60, 90 triangles and their ratio. So like if you know that's 30 degrees, this is like your x, and I don't want to use x, so I'll use a instead. So that's like a, and then you multiply the other side by square root of 3, so a square root of 3, and then this last side's 2a. So we have 5 square root of 3 equals a square root of 3. So a has to be 5. So this little piece there is going to be 5. That means the entire radius right here, going in a different direction, that's got to be 10. Alright, now if a radius is 10 and then we're trying to figure out, I guess they need to put little endpoints kind of like that, but if we're trying to find the diameter, well then it's just double that. So y equals 20 for that. So that one a little bit different there. Last one here. Now this might actually look a little bit different than the one you have marked here in your notes. And the reason being I wanted to highlight on something here. You'll see some problems that look just like this here. And then people say, well, man, I don't know how to use those numbers to find x. And what you got to do is every now and then is maybe redraw another radius. Like we know every single radius has got to be x there. So maybe if we can draw myself a right triangle inside of your circle, we can use the dimensions to go find your radius there. So that's actually what y'all have marked there. So I kind of whited it out, I guess. So you have a right triangle. You have a perpendicular angle, therefore it's got to be perpendicular bisector. Okay, so this side here has got to be 4. And then you can go do Pythagorean theorem, put an x right there, and then we can say x squared equals 3 squared plus 4 squared. It is a 3, 4, 5 triangle, so when you do solve it out, it comes out as x equals 5 if you know your Pythagorean triples. And I think that is it for today.